Okay, hello everyone. My name is Nabizada. My topic is on the mechanical properties of laser powder bed fusion 316L containing porosities and charged via gaseous hydrogen. This is a collaboration between UGent and UC Leuven in Belgium and supported by FPS Economy. First, this is the content I'm going to present, a brief introduction about the topic, and then some explanation about materials and methods we use, some preliminary results, and then in final stage, summary and outlooks. Okay. Owing to acceptable hydrogen embrittlement resistant, 316L is a good candidate for producing pressure vessels, hoses, valves, which are used in refueling stations and petrochemical industry, the environments containing hydrogen. However, 316L possesses relatively low yield strengths, which restricts its applicability in high pressure hydrogen gas. So to address this issue, additive manufacturing technologies has gained a growing interest. And as you can see in this graph, the yield strengths of products manufactured by additive manufacturing is quite higher than products which are manufactured by conventional methods. But the question is, how would be the performance of these materials, specifically the grade of 316L in contact with hydrogen, and if there is any hydrogen embrittlement, which factors affect this mechanism. Among the AM technologies, laser powder bed fusion is more common and popular. This is a schematic of this process where a laser is used to melt a progressively added layer of powders to form a 3D shaped product. But due to some characteristics of this technique, like internal defects, like rapid cooling and directional solidification, the presence of some internal defects like pores is inevitable. So the other question is how these effects, how these pores change hydrogen diffusivity and hydrogen content in these materials, leading to difference in mechanical properties and hydrogen embrittlement mechanisms. So the motivation of this study is to answer these questions. Okay, going through the material and methods, we printed different samples with different variable process, and we measured hydrogen. We measured the density of these samples via hydrostatic weighing and some cross-section image analysis. We selected 2 batches of these samples. The first batch with the highest porosity fraction, and the second one with the lowest porosity fraction. And we charge these batches in autoclave to introduce hydrogen inside the samples with the condition you can see, and followed by some tensile mechanical tests. And we analyzed hydrogen behavior via extraction techniques and TDS method. Also, microstructural evolution is analyzed via SEM, XRD, and EBSC. So preliminary results. First, you can see the cross-section of the first batch and second batch, and the first batch shows a density, a porosity fraction of almost 0.1%, and the second one shows almost 1% porosity fraction. The initial microstructure of those batches is quite similar, and with the close grain size and grain size distribution, we have federally like prolongated grains along with the building direction, and KM map and KM intensity distribution also shows that dislocation density is very close in those batches, and we can infer that if there is a significant difference between hydrogen embrittlement of these two batches, that should be because of porosity presence and not microstructure. This is the engineering tensile stress strain curves of those batches in uncharged and charged condition. The first point we can obtain from these graphs is the mechanical properties of material with lower porosity fraction is much better than the other one. And there is a slight increase in tensile properties, yield and UTS, which is linked to the solid solution strengthening of hydrogen. And also the ductility loss for the first batch is quite lower than the second batch. So we calculated the hydrogen embrittlement index for both materials. You can see the hydrogen embrittlement index for the material with higher porosity fraction is almost more than 4 times that of the other one. Okay, this is the fractography of material with lower porosity fraction. You can see in the images above, after charge, the first point is necking is obvious for both uncharged and charged condition, and in the fracture surfaces we see dimples are present. So the actually fracture mechanism of this material is ductile, and this is actually correspond to small changes of ductility after hydrogen charging and hydrogen embrittlement resistance of this batch. For the second batch, we can see there are some coalescence of cracks in images above. Also, after charging, the fraction area of ductile mode decreased by hydrogen charging, and the brittle features are more pronounced in hydrogen charged samples. So here we have a mix of ductile and brittle fracture because of presence of pores and also dimples. Hydrogen, we can infer that hydrogen actually triggered the crack in propagation, and the pores act like a crack initiation site in this material. This is the actually reason why hydrogen embrittlement in this material is much more significant than this first batch. Okay, this is the actually EBSC maps of the first batch. we did interruption tests on 30% of engineering stress strain curve to compare the microstructural of both uncharged and charged condition. And you can see the phase maps superimposed on the twinning maps. Via charging, the fraction of twinning increased, but there is no clue of martensite. Even we evaluated fracture samples, there was no clue of martensite. We actually here we can infer that enhanced deformation twin and phase stability of this material are the two main reasons of hydrogen resistance of this material. Enhanced deformation twin can positively contribute to work hardening of charged material, and it also can be a trapping site to actually hinder hydrogen mobility to the matrix. But for the material with high porosity fraction, we also evaluated the microstructure in interrupted samples. Also, there is no martensite formation during tensile tests, and hydrogen here also enhanced the fraction of deformation twin. You can see the work hardening rate of charged sample is higher than uncharged in stage 2. But the point is actually Km intensity distribution shows that hydrogen charging cause an inhomogeneous strain contribution and dislocation density compared with uncharged condition. So we can conclude that here porosities act like a stress concentration site, and hydrogen can be trapped inside the pores or at the interface of them with matrix, and accelerates the hydrogen embrittlement. And hydrogen can trigger this process via strain localization in the microstructure. To actually highlight the effect of porosity and minimize the effect of microstructure, we annealed samples at this condition, and we evaluated the TDS peaks of both microstructures and both conditions. You can see that first of all, heat treated increased the hydrogen diffusion coefficient in both material. That's because of the decrease in residual stress and dislocation density, but porosity presence actually increased the diffusion coefficient and also the hydrogen content in these materials, because they act like a short circuit diffusion paths in the microstructure, and also they act like reversible traps. So this is an ongoing research. Until now, we can conclude that SLM 316L with a low porosity fraction exhibits reduced hydrogen embrittlement. Pores can localize deformation strain and trigger hydrogen embrittlement. Hydrogen enhances twinning activity and promotes brittle fracture. Pores act reversible traps, increasing the hydrogen diffusion coefficient and also hydrogen content. The impact of hydrogen trapping in pores is more significant, the dislocation cells. We're gonna do some analysis on porosity size, connectivity, and distribution to clarify the diffusion process. Also, doing some experiments on hydrogen desorption process to elucidate the role of trapping for porosity, and comparing the mechanical properties in different charging conditions would be the third outlook. Thank you very much for your attention. If there is any question.